All right, drum roll, please. We are now at the point in our year where we are going to start bringing things together. At this point, we are going to bring thermochemistry and bring it together with, you guessed it, equilibrium. So, you kind of maybe saw it in the last video coming because we talked about ln of q, but we're going to bring it together. We're going to be able to relate our equilibrium constant and our delta G. We probably already know a little bit about this, but let's go ahead and see what we got. So here we go, our first one there. When Q is less than K, ln of K is going to be negative and delta G is going to be positive. So we have oh, yes, delta G is going to be non-spontaneous, all right, in this direction. So non-spontaneous, which makes sense with what we said. When K is less than 1, we have very few products, right? Okay, awesome. When K is greater than 1, that means our ln of K is positive and delta G naught of reaction is negative, so that means it's going to be spontaneous in this direction. All right, and when K equals 1, ln of K is 0, and delta G naught of reaction is 0, and so we are at equilibrium at these conditions. All right, which is kind of exciting. It's kind of exciting to bring this all together. Hopefully you're excited as well. So we're going to bring these babies together. So we're going to use tabulated free energies of formation to calculate the equilibrium constant for the reaction at 298 K. So we're going to use that formula right there. Let's put that on our paper. All right, and remember, we're probably going to want our delta G naught to be in joules, so we'll get to that point in just a couple of seconds. So remember to find delta G naught. We're going to take products minus reactants, right? So we're going to take 2 times whatever NO2 is, minus 1 times, put in brackets, not that it's super necessary, but N2O4 is, all right? So 2 times NO2. NO2 is 51.3, and N2O4, 1 times 99.8. So our delta G naught of reaction is going to be equal to 2.8 kilojoules, which we're going to say 2,800 joules because that's going to help us plug it in over here. So on this side, we're ready to plug it in, but we've got that ln of K to kind of worry about, right? So if we solve for that side for ln of K, and we're going to divide by negative RT, right? We get ln of K is equal to delta G naught of reaction over negative RT, all right? And we're ready to plug all this in. So we're going to take boop, ln of K is equal to 2,800 joules, right, over negative 8.314 times our temperature, which is 298. They've been real nice with us and doing that. All right, so we're going to get ln of K is equal to negative 1.13. Now, at this point, we have to get the ln out, right? And we can just take the inverse natural log, if that's what we're calling it these days, or the e to the x of negative 1.13. And so our k is going to be equal to negative, or not negative, 0.32. K is equal to 0.32. Now, does that make sense? So it's going to be, it's greater than 1, but not much greater than 1, right? So it is non-spontaneous, right? Which makes sense because our delta G is so small, but it's positive. All right. Hope that makes sense. And that is the end. I'll see you guys on the next one, chapter 20.